Hey, my friends, it's another day, another lesson of wonderful mathematics, and we're going to introduce a new function to you called logarithms. Some of you may have seen some logarithm stuff in science classes, may seem kind of out there to you then because we really haven't talked about it much in math class, but we'll get to exactly what a logarithm is in just a few minutes. All right, so hopefully it's a beautiful day outside, you're having a good time. All right, but had to take a break from all that other fun, do something a little bit more exciting, a little bit of fun, a little bit of math. And we're going to start with 4 problems here in our opener. All right, just to get you thinking about some specific things. So, what I would love for you to do right now is work problems 1A, 1B, 1C, and 1D there. Get your answers. So, pause the video, give those 4 problems a shot, and then we'll talk about why we're having you do those. All right, so let's go through and talk about these 4 problems in the opener. And I'm just going to flip to where I have my work. All right, so to solve the first problem, we have to take the square root of both sides, right? And that would give us the plus or minus the square root of 25 times 2. And we've talked about reducing those radicals this year. So hopefully you remembered a little bit of that. And if not, here's a quick refresher, right? So that gives us plus or minus 5 times the square root of 2. All right, so 1b. So how do you undo the cube root of something? You cube it. All right, just like the same way I undo a square root is that I square something. So if I cube both sides, that leaves me x here. And if I cube -3, that gives me -27. All right, so if I look here, I have x divided by 3. Well, how do you undo dividing by 3? You multiply by 3, and that gives me x equals -12. Now, this was maybe the one that some of you had the most trouble with. Been a while since you think about or thought about your trig functions way back in geometry, about this time last year, actually, probably for most of you. All right, so if I have sine of theta equals 3/5, the way I solve for theta, or the angle, is I do the sine inverse of 3/5. And if I do that on my calculator and I'm in degree mode, I get 36.87 degrees. And so these might all 4 seem kind of random. And in a way, they are random. And they're not really tied to anything except for the idea of this, right? So how did we solve each of those problems, right? So what did we have to do? We had to do the inverse of that operation in order to solve. So we had to take the square root to undo a square. We had to cube to undo a cube root. We had to multiply in order to undo division, right? We had to take the sine inverse to undo the sine of an angle. So the whole idea, right, is that this idea of inverses, right? So in mathematics, every operation has an inverse, right? And that's really a big idea. There's a way to undo everything, all right, mathematically, right? And so that's where the idea of a logarithm comes in, because if we have an exponential, it has to have an inverse or an opposite as well. And that is what a logarithm is. A logarithm is the inverse to an exponential. So let's just do some basic things here with our graph here of f of x equals 2 to the x. All right, and talk about like how that leads into what a logarithm is. And so all we're going to do real quick here is just create our table of values, and I'm going to draw our exponential graph here, and then we're going to talk a little bit about that and how that ties into a logarithm. So we have our x values here, so I'm just going to go from -3 to 3. All right, so 2 to the -3rd power would be 1/8. All right, 2 to the -2 would be 1/4. 2 to the -1 would be 1/2. 2 to the 0 would be 1. 2 to the first power would be 2. 2 to the second power would be 4. And then 2 to the third power would be 8. All right. And now if we think about what we did with the graphing last time, there's no vertical shift, there's no horizontal shift. So I know my horizontal asymptote is going to be the x-axis here. All right. We know the base is greater than 1, so it's going to be an increasing function. I'm not, just to save a little bit of time, I'm not going to graph all these points. I'm just going to graph a handful. So -1, 1/2, 0, 1, 1, 2, 2, 3, 4. All right, and we know that it's going to look like this, right? Okay. So now, that's our exponential function, right? So now let's think about what we talked about way back when we've talked a little bit about our different types of functions. We've talked about inverses, And what do we know that happens with the domain and range of inverse functions? So if you need to, pause the video, think about that a little bit, all right? But it's really, really important that you understand this moving forward. Okay, so what do we know about domain and ranges when we do inverse functions? And that we know that they switch, right? All right, which is a really, really important thing, right? Okay, so if this is the domain of our exponential and this is the range of our exponential, they're going to flip. And this is going to become the domain of our logarithm. This will become the range of our logarithm. All right, and I say swith, they swith. I left a C out of there somewhere. All right, switch. There's a C in there. All right, okay. So I was kind of right like I speak sometimes, so I apologize. So now what we're going to do is, because we know the domain and the range switch, what we're going to do is we're just going to take this domain and range and we're going to switch them, and we're going to create the picture of our inverse first, and then we'll kind of talk about some properties and some other things that are associated with that. So I'm going to flip right over to the next page of notes. Now what I've done here, if you need to pause the video to catch up, is I've already flipped the domain and the range from the prior problem, just so you guys didn't have to sit there and watch me kind of write it again and again and again. So if you need to pause the video and catch up, do that. Otherwise, what I'm going to do now is I'm going to start graphing, right? So this is now going to give us a picture of our inverse of an exponential, which we call a logarithm. So notice, I'm only going to go to the right 1/8, and I'm going to go down 3. All right, so to the right 1/8 and down 3. So that's really tight right here. So really, okay, then I'm going to go to the 4th, and I'm going to go down 2. So that's still pretty tight. To the right 1/2, down 1. To the right 1, and I'm not going to go up or down. To the right 2, up 1. All right, to the right 4, so 2, 3, 4, up 2. And then to the right 8, so 5, 6, 7, 8. Almost think we're about to dance. All right, there we go. And then there's our graph. And so what you can see is it comes right down the y-axis this time. And let's see, I almost hit that point. Kind of got that point, there we go. All right, and we kind of go this way, right? All right, so there's our graph of a logarithm. So notice it, if we were to spin and rotate, it looks a lot like an exponential graph, right? But it's kind of turned on its side. It's kind of like it's fallen over, which is what it's supposed to look like. So now let's try to make some connections. So we have our picture here, right? And so we're going to ask some questions about f of x equals 2 to the x. I'm just going to run back here and we'll take a look at this, and I'll ask these 3 questions and we'll go back and write them down. All right. So now let me move this back up so you guys can see it. I was going to try to scroll this down just a little bit. So when we look at this, notice once again, we talked about this last time, that the domain for every exponential will be all real numbers. So the domain is all real numbers. Our range for this is based on our horizontal asymptote, which is y equals 0. And so our range is 0 to infinity. So now let's go back and jot that down. So the domain we know here is, all right, for all real numbers for every exponential. We know the range for that mother function, all right, that mf'er is 0 to infinity. All right, and then we know that the horizontal asymptote was y equals 0. All right, now notice, let's now look at the same 3 questions, but for our inverse function, for our logarithmic function up here. So notice now, all right, when I look at this graph, all right, notice my domain is now limited. So notice we get a vertical asymptote here, right? So nothing goes past x equals 0. All right, so now we kind of jump here. What type of asymptote does it have? It has a vertical one, and its equation is x equals 0. And notice that influences now our domain, because now the domain is 0 to infinity. Well, notice this graph is going to keep going down forever. It's going to the right and up. It's not going up very fast, but it's still going to continue up and up and up forever. So the range is all real numbers. And now this should make sense, because if these are inverses, right, we know the domain and the range switch. So the domain here was all real numbers. The range for our inverse should be all real numbers. The range for our function was 0 to infinity. The domain then has to be 0 to infinity. But everything is opposite when we do inverses, right? So notice we had an asymptote at y equals 0. What's the opposite of that? It would be x equals 0. All right. So hopefully you're starting to see some of those connections, right? So right now, if we had to graph every exponential, we know the range, the domain would be all real numbers. So what we now know about every logarithm is that the range is going to be all real numbers. When we graph an exponential, we know we're going to have a horizontal asymptote, and then our range is going to be based off of that. Now, consequently, we're going to have a vertical asymptote, and then our domain is going to be based off of that. Okay, so now let's talk about notation and representation of that. So now, when we think about f of x equals b to the x, all right, that's our exponential function. We know the domain, right, is the powers, right? So I'm putting in the powers of the base here. And the range is the result, all right? So my input would be 2, my output would be whatever the base is to that second power. Now, here's the notation, all right, for a logarithm. We abbreviate that with log. In the same way we kind of abbreviated sine with sin or cosine with cos, right? So this log, all right, means logarithm. And then notice whatever base we have here, we still have that same base here, all right? Now, here's what we have to understand. This x, right, is the output, right, of an exponential function, all right? And we'll see kind of what that looks like a little bit more as we go through some examples here, all right? We start looking at what that looks like as a full equation, all right? So that's the big idea, that we need to understand that because the domain and the range switch, so the range is the output, right, is the result. That's what the domain is here. The domain here are the powers. Well, that's what the range has to be. It has to be the powers, okay? So if we have base 3 here, we're going to have base 3 here, all right? And those all are going to match. Okay, so that might seem like a little out there right now, but hopefully as we see a few more examples and we go through some problems, it starts to click in place for you. So now let's look at, all right, some examples here. So let's look at some exponentials. So hopefully you guys all agree that 2 to the third power is equal to 8. All right? So 2 to the third power is equal to 8. So now when we think about how do I represent that as a logarithm? Well, we'd have log, and since it's base 2 here, it's base 2 here. Now remember, the power is the input here. That means that has to be the output of the logarithm. So notice it's log base 2 of 8 is equal to 3. So you can see that the output here is the input here. The input here is the output here. All right, so 4 squared is equal to 16. So we have log base 4, so the bases have to match. Okay, the input is 2. That means the output is 2 here. The output is 16 here. That means that's the input here. All right, and so that's really what it would look like, right? So 3 to the 0 is equal to 1. Log base 3 of 1 is equal to 0. 1/2 to the negative 5th power is 32. So log base 1/2 of 32 is equal to negative 5. All right. And so what this generally means, if we think about it in terms of just generics here, if y is equal to b to the x, that means log base b of y is equal to x. So here's the biggest thing that you can remember, is that when you're solving for the logarithm, you're really asking yourself, what was the original power? What power gives me this number? All right. So for example, if I had log base 5 of 25 equals 2x. All right. This is what this is really saying is what power of 5 gives me 25. Okay. So the logarithm is asking for what power, all right, of your base gives you this number right here. So this means that x would have to be 2. All right, so just remember that the logarithm is asking for what was the original power of your exponential. Okay, now there's 2 special logarithms that we need to talk about. So almost every time when you look at a logarithm, it's going to have a number for the base. All right, so log base 2, log base 3, log base 4, log base 1/2, log base 5. But there are 2 exceptions to this. So one is the common log, right? We are base 10, all right? And so when we see base 10, we have 10 squared equals 100. Well, we just see log. You're not going to see a number down here. They're not going to put base 10 because that is our number system. All right, so when you just see log, that means you're working in terms of base 10. Now, we also have introduced the letter e, or the number e, I should say, all right, in some of our application questions earlier in our application lesson to start this unit. We call that the natural logarithm. All right. So we represent that with ln. So when you see natural log, so instead of doing this, right, log base e, right, instead of writing it like that, which maybe is a little bit confusing, they just do natural log. So you're going to see ln, all right, of like that. But anytime you see ln, that means the base is e. All right, so let's now jump into working on what this means and interpreting those. And so there's going to be a little back and forth here as we go through some examples to kind of help you understand, all right, what a logarithm is and what each piece represents within that logarithm. So let's look at some examples here. All right, so let's look at 3a here. All right, let me switch colors here. I think I'll go with purple. Let's go with purple. Doesn't it feel a little like a purple time right now? All right, so we want to know what x is. Now, for some of you, you might be able to see this and just click right through it, right, and write it down. What I'm going to do is I'm going to write it as an exponential right now for all of us. That way we can kind of see exactly how all the parts transfer, and that will hopefully help with your understanding. So notice this is base 2, so I know my exponential would have been base 2 as well. Now, this is asking for the power. So this is saying 2 to what power is 64? So 2 to what power is 64? Well, now that means that x has to be, so I can go through my power. So 2, 4, 8, 16, 32, 64. And I'm counting on my fingers, not that you guys can see that. All right, but I had 6 fingers up. All right, so that means it was the 6th power of 2. So that's what x would be. Now, you don't necessarily have to write this out, but for some of you, this might help you translate, at least so you get familiar with everything. All right, so let's do 3b together. So once again, it's log base 7 of 49 is equal to x. So it's base 7, so it's base 7. And then 7 to what power is 49? All right, so 7 squared is 49. So that means our power had to be 2. All right, so what I'd like you to do now is just pause the video and do 3c and 3d and then check back with me. All right, so hopefully you did 3c and 3d. So let me click over here. I did those on the side. So once again, this says 9 to what power is 1? Well, that means it had to be 9 to the 0 power. Okay, so this is 1/3 to what power is 1/27th? And I just wrote it out a little bit here, so maybe to help you translate a little bit, but it means that we'd have to raise 1/3 to the 3rd power, right, to get to 27. All right, so hopefully this is starting to kind of sink in a little bit, make a little bit better sense for you. So let's continue with these kind of problems. So now let's look at problems 4 here, and let's do 4a and 4b together. And it's the same idea, but now notice our variable's in a different spot. Okay, so now it's saying, okay, what is this value? So once again, this would be 7, and then to the negative 2 power is equal to what? Right? So 7 to the power of negative 2 is equal to what? And that would mean that x would be 1 over 7 squared, which would be 1/49. All right, now here's one of those special examples. Notice this is log of x is equal to 3. And if it's just log, that means we are in terms of base 3. So that's really 10 to the 3rd power is equal to x. And you could leave it like that if you want, or you could just write it out that, okay, so 10 to the 3rd power would be 1,000, and that's what x would be. Okay, so once again, what I'd like you to do is try 4c and 4d. All right, so let's jump in. Once again, I have those written out right over here. All right, so this would be base 12 to the 144th power is equal to x. I think we probably just want to leave it like that. I don't think we want to try to multiply that out. That's a really big number. All right, might make your calculator freeze up. So we can leave it like that. Here we have 6 to the negative 1st power is equal to x. And this is a little bit easier. So 6 to the negative 1st power would just be 1/6. We can simplify that pretty easily as well. All right. So let's look at a couple more together. There we go. So let's look at 5a and 5b together. And hopefully you're starting to see how this is all fitting, all right, and fitting together for you. So once again, now notice this time we're looking for what base of the logarithm, okay? So now this is the base something to the third power is equal to 64. All right, so what power or what base to the third power is 64? Well, in this case, that would be x to the fourth power, right? So 4 to the first power is 1, 4 squared is 16, and then 4 to the third power would be 64. And a very similar fashion here, right? So x to the negative fourth power is 100 or 1 over 625. All right, so I had to find something to the fourth power that is 625, and that something would be the fifth power, all right, or excuse me, the base 5, and so that means that x has to be 5, all right, because 5 to the negative fourth power is 1 over 625. All right, so once again, pause the video, you try 5C and 5D, and we'll see how you did. All right, let's take a look at these two guys. All right, so once again, x to the second power is 1 over 64. All right, so that means I must have had 1/8, because 1/8 times 1/8 is 164. Okay, what to the first power is 9? Well, what to the first power is 9? That means 9 to the first power has to be 9, so our base had to be 9 here. So hopefully you're seeing this and it's transitioning pretty well for you. We just have a handful more problems here. Let's do 2 more together. Now, the nice thing is after everything that we just did, all right, these 2 problems, all right, should hopefully be very quick for you. So notice now it says convert this to an exponential equation. Well, that's really what we were doing here. We're just not trying to solve. We just want to write it as an exponential. So log base 11 of x is equal to y means that our base is 11. The power is y, and the result is x. All right, on 7a, we want to convert it to a logarithmic equation. Well, so 8 to the power of y is equal to x means that we're going to have log base 8. Now remember, the result is here, and it's equal to whatever the power was. So there's 6a and 7a, and you guessed it, you're right on. Do 6b and 7b. Pause the video, give that a shot, and let's see what you did. All right, so looking at 6b and 7b then. All right, so if I look at 6b, now once again, if I have just log, that means we're in base 10. So this is 10 to the 7th power is equal to 3. All right, which is not a true equation. So I'm not sure where I stole that example, but that's not a good example because 10 to the 7th is definitely not 3. All right. So moving on past that bad math there, and we have e to the third is equal to x. Now remember, once our base is e, all right, we represent that with the natural logarithm. So that's ln of x would equal to 3, like so. And that, my friends, wraps up this lesson, wraps up your introduction to logarithms. All right, so take a look at the homework. All right, work through that. Let us know if you have questions. Remember, you can email us. You can come during our office hours, hop on the Google Chat, Zoom, or Google Hangout, whatever we're doing for that time. Let us know if you have questions. All right, take care of yourself, take care of each other, and we'll see you soon.